El profesor Arthur Miller es profesor de Historia y Filosofía de las Ciencias en University College de Londres y ha intervenido en diversas manifestaciones, programas diversos sobre el tema de la historia de la ciencia y la filosofía de la ciencia, ¿no? Hoy nos va a ofrecer una conferencia que es Empire of the Stars, como pueden ver ahí, en la que, bueno, refleja sus últimos trabajos. Y sin más, le doy la palabra al profesor Miller.
Thank you. I'd like to thank Dr. Pedro Eschenik for inviting me and Dr. Unai Ugaldo for arranging this, kindly arranging this lecture for me, and to all of you for going beyond the call of duty and hearing me talk. Now, it's very difficult to imagine a black hole. Who knows? Maybe it looks something like this. They seem to pop up everywhere these days, even in the world of politics and finance, and who knows who the black hole is there. And actually, a black hole is a well in space into which a star has fallen. It's a terrifying kind of well because nothing can escape from it, not even light. And this can be rendered spectacularly by an artist. The immense gravity, here's the black hole, and inside there's a once robust, huge star that's undergoing an eternal collapse. And the immense gravitation of this collapsing star snares gas particles in the immediate vicinity and forces them into forming a swirl, much like water going down a bathtub drain. The gas particles closest to the black hole move fastest, rub up against each other, they become heated up, and then blaze with the light of 1,000,000 suns before falling in. What might happen to a person who falls in? Well, let's consider a hapless astronaut who ventures a bit too close to a black hole and who falls in feet first. What will happen is that the astronaut will feel a tug much harder on his feet than on the upper part of his body, and soon he'll become stretched more and more and will become spaghettified until he becomes torn apart. The term black hole is used in our everyday vocabulary, but it wasn't always like that. And today I'd like to tell you the story of how this came about, and to do that we must drop back 70 years to when the world's most famous astrophysicist, Arthur Stanley Eddington, and a little-known 24-year-old Indian colleague, Subramanian Chandrasekhar, Chandra, clashed at the Royal Astronomical Society over the fate of the stars. And what I'd like to do today is to tell you about the background to this fracas, what happened on that fateful day of 11 January 1935, how it affected both their lives and the course of astrophysics, and how it was resolved some 40 years later. Let me begin by introducing the protagonists, Eddington, Chandra, and the white dwarf star Sirius B. Now, Eddington set out his immensely popular and successful standard model of the stars in his classic 1926 book, The Constitution of the Stars. A few blemishes remained, which he forthrightly pointed out, and among them was what happens to a star after it burns out its nuclear fuel. There were two options available in 1926. It could either blow itself to smithereens or become a white dwarf star, a sort of object that seemed to lay outside the domain of the standard model. Now, white dwarfs pack the mass of the sun into a volume the size of the Earth, and so led to densities of about 60,000 grams per cubic centimeter. This was huge at the time. Indeed, if a teaspoonful of white dwarf material would transfer to the Earth, it would weigh 6 tons, about the size of about the amount of a good-sized elephant. To this absurd density, Eddington quipped, well, that's just ridiculous. They were also very curious in the sense they were hot but dim. That is to say, they were measured to be about 10,000 degrees Kelvin and plus 10 in absolute magnitude. How could this be possible? By 1914, 2 of them had been identified, O2 Eridani b and Sirius b. By 1926, several more had been found, and the situation had to be taken seriously. Now, at the time, astrophysicists considered a star to be a sphere of a perfect gas which maintains its equilibrium under a delicate dance between a balancing act between the sum of the gases of the star's outward radiation pressure due to its light streaming out like a hurricane, its gas pressure, which one calculated from the perfect gas law of classical physics. And these two pressures had to balance off the relentless inward push of gravity. Now, since a white dwarf is dim and becoming dimmer, its radiation pressure is decreasing. Soon the only thing left is the gas pressure, which is not sufficient, and gravity wins, and according to the standard model, the white dwarf star should be crushed into an infinitely tiny, infinitely dense point. As Eddington put it, in his book, Constitution of the Stars, the star seemed to got itself into an awkward fix. If it cooled, it would presumably revert to terrestrial density, but that meant that the star must expand to 5,000 times its present bulk. And expansion requires energy doing work against gravity. And the star appeared to have no more energy available. What on earth was the star to do if it was continuously losing heat but had not enough energy to get cold? Now, Eddington focused his attention on the white dwarf for which the most accurate data existed, Sirius b, all but obscured by its binary companion Sirius A, the brightest star in the night sky. In 1914, Eddington had been somewhat incredulous about Sirius B's huge density. In 1926, he was willing to entertain the idea, and indeed he set out to ingeniously verify it using Albert Einstein's general theory of relativity, on which he was a world-acknowledged expert. And in this, he used the gravitational redshift. He guessed that changes in the perfect gas law would be required, but nothing very drastic. But this turned out not to be the case. Eddington's colleague, shortly after publication of Constitution of the Stars, Eddington's colleague at Cambridge, Ralph Fowler, realized that when a huge number of electrons is squashed together, like in the inside of a star, then quantum physics must be used, not classical physics. Here is Fowler, who literally dwarfs Heisenberg and Pauli, who's standing next to him. Fowler is as big as the two of them put together. As Chandra described Fowler in 1930, a big man in every sense of that phrase. Now, using quantum physics meant that Pauli's exclusion principle comes into play, and Pauli's exclusion principle asserts that no two electrons with exactly the same property can occupy the same quantum state, properties such as location, speed, and spin. Electrons are asocial things. They like to stay as far apart as possible. Fowler discovered that this quantum property of electrons meant that there was a limit to which a gas of electrons could be compressed. Once it's reached that limit, the gas falls into what's called a degenerate state, having nothing to do with moral axioms, and it responds by producing an outward degeneracy pressure, and the clump of gas becomes rock hard. And in this way, Fowler found a white dwarf star is able to expire as an inert rock in the sky, rather than being crushed into nothingness. At the end of his paper, which Fowler wrote in November 1926, Fowler stated, "I'm satisfied," and so was Eddington. Now, by 1930, Eddington's fame had reached its height. His popularizations of science were widely read, his philosophy discussed, his cosmological considerations highly regarded. Since he had verified Einstein's general relativity theory in 1919 by observing the deflection of light of stars near the sun, he had become almost a household name. And indeed, he had verified Einstein's theory a second time with his work on the gravitational redshift and Sirius B's high density. He was also immersed in work on a theory of everything, which he called his fundamental theory. It was to be the culmination of his life's work, a quest for the truth, which was extremely important to Eddington. This theory would eventually, in Eddington's view, transcend physics into biology and even into the workings of the mind itself. In short, everything was going excellently for Eddington, and then Chandra appeared at his door. Chandra had spent a golden youth in Madras. Here is the great Marina Beach, where Chandra and his brothers on hot evenings would cycle to escape the searing heat of the city and take in the cool breezes blowing off the Bay of Bengal. They would lay on the sand on their backs and contemplate the sky, and Chandra would lecture to them on literature, science, and philosophy. In the background is a dome of Presidency College, which Chandra attended. Chandra was raised in a free-thinking, upper-class Brahmin household. His father, affectionately called Babuji, was a typical Indian father of the time, stern and aloof, but caring. And Chandra's prodigious abilities in mathematics, which were noticed early on, and were inspired and pushed by family members, including his rather fearsome-looking uncle C.V. Raman, India's first Nobel Prize winner in physics, and a powerhouse in Indian science and academic politics. In 1930, at the age of 19, Chandra graduated Presidency College, top in his class. By this time, he had already published several very complicated papers applying quantum statistical mechanics to the stars. And indeed, 2 years earlier, at the age of 17, he had read and mastered Eddington's book, Constitution of the Stars, and become intrigued with Eddington's discussion of white dwarfs. Could it be that the fate of white dwarfs was the same as the fate of a star like Betelgeuse in a parable of Eddington's? Betelgeuse is a supergiant, a star which is as big as the Earth's orbit about the sun, but is also 100 million times less dense. But what if, Eddington mused, Betelgeuse was as dense as the sun, maybe even as dense as a white dwarf? In that case, Eddington wrote, the mass would produce so much curvature of space-time that space would close up around the star, leaving us outside, that is, nowhere. In other words, the star would fall into a hole in space-time. In the spring of 1930, Chandra discovered Fowler's paper, in which Fowler had apparently solved the problem of white dwarf stars. Chandra was especially struck by Fowler's paper because, after all, by this time, Chandra himself was quite an expert on quantum statistics. But he had to put Fowler's paper aside. At this time, he had to revert from being a researcher on the frontier of physics to an undergraduate student. Final exams were looming, which Chandra passed with flying colors. And indeed, he left in July 1930 as a youth of 19 with a government fellowship to study physics at the only place that existed for him, namely Cambridge University, where Ralph Fowler and Arthur Eddington resided. It was to be a great adventure, an enormous undertaking for the young man, because besides journeying to one of the world's great centers in science, he was leaving behind a way of life and the young woman with whom he had fallen in love, Lalitha Daraswamy. On board ship, while crossing the Arabian Sea, Chandra had the time to take out Fowler's paper and look at it closely, and to his amazement, he found out that in 4 years, nobody had noticed that Fowler's solution was approximate, because Fowler did not include special relativity. Including special relativity allowed Chandra to formulate a much more exact theory of a white dwarf star. And it produced an astounding discovery, namely that white dwarf stars could not exist with a mass greater than a certain limit, which was about the mass of the sun. Chandra made this discovery in minutes, recalling his immense calculational powers. The next question was what might happen to stars which expire with a mass greater than that limit. Well, Chandra thought no more about this for the moment, but felt sure that he would be welcomed at Cambridge by Eddington and Fowler as a genius, a hero, just as he had been considered in India. But what happened was very different. Fowler was wary of Chandra's result and passed it on to his colleague at Oxford, Edward Arthur Milne, who had his own ideas about the fate of stars. Milne took one look at Chandra's result and considered it to be another contribution to his own theory. According to Milne, stars are a nesting of degenerate cores. The outside is a gas, the outside envelope is a perfect gas, and inside there's Fowler's non-relativistic degenerate core and Chandra's relativistic degenerate core. In Chandra's theory, a white dwarf is comprised of a gas of electrons which is in a relativistically degenerate state. And these equations, let me just mention it because it's rather amazing. They're called equations of state, and they relate the pressure of a gas to density and temperature. For a perfect gas, the pressure is related to the temperature, but miracles occur because when you consider quantum mechanics, at effectively zero temperature, you still have a pressure, the degeneracy pressure. And Fowler's theory, the pressure is proportional to the density to 5/3 power. In Chandra's theory, the pressure is proportional to density to the 4/3 power. The main point is, if gases were comprised of a perfect gas, like in the Standard Model, when their temperature went to zero, they would be crushed by gravity. There's no more gas pressure. But not so when you consider quantum physics. Now, when the star comes crashing through each one of these degenerate cores, and it even crashes through Chandra's core, well, there has to be another one. And at the end, there even has to be an innermost, absolutely incompressible core, because after all, how could something as big as a star collapse to nothing? When Chandra arrived in Cambridge, like everybody, on the second Friday of every month, he traveled down to London, to Burlington House in the Royal Astronomical Society, where he witnessed something that people stood on lines to see, namely a battle of the giants, Eddington versus Jeans and Milne, a battle that Eddington always seemed to win. And Chandra was mortified. He was anxious to avoid becoming a pawn in these battles. Indeed, this is rather amazing. Instead of comparing himself with other students, Chandra compared himself with Eddington, Jeans, and Milne and Fowler, and as well as with a physicist with whom he idolized at Cambridge, Paul Dirac. That being the case, it's understandable that he felt increasingly unsure about his own scientific abilities. He also struggled to come to terms with Britain, its people, customs, food, and in England we don't have weather, we have climate. And all of this differed dramatically, clashed dramatically with what Chandra was used to from his hot, sunny, and relaxed homeland of South India. And he also had to suffer constant reminders that he was a colonial, and even worse, an Indian. But despite Chandra's constant lapses of confidence, by 1933, when he received his PhD, he had published 11 authoritative papers on the shape and constitution of stars, and had spent periods of time at Max Born's Institute in Göttingen and Niels Bohr's in Copenhagen. All of this led to his being elected a Fellow of Trinity College, which gave him 3 more years full-time to do research. Here he is, a handsome, young, earnest man, now, again, full of confidence, at least for a while. And he was finally confident enough to return to his discovery of his theory of white dwarfs. He began to consolidate results that he had achieved in the years since 1930, and by fall of 1934, began putting together a series of papers in which he honed his theory to a high degree of mathematical rigor. Eddington was even visiting his rooms several times a week to see how he was doing, and suggested to Chandra that he present his results at the Royal Astronomical Society meeting of 11 January 1935. And Chandra was all excited about this, of course. The day before the meeting, Chandra was surprised to learn that Eddington had arranged for himself to give the lecture following his on the same topic, relativistic degeneracy. This was puzzling, but Chandra thought no more about it. Let's drop back in time to the original Royal Astronomical Society lecture room, a few doors down from the one that exists today. Here it is, March 1935. James Jeans is holding forth on Fred Whipple. Let's wind the clock back to 11 January and imagine Chandra sidling down the aisle of this windowless room, by that time 2 hours into the meeting, as hot as the tropics. Indeed, at a previous meeting, someone was heard to whisper out loud to himself during a lecture on whether there's air in Venus, never mind Venus, is there any air in here? Chandra, in the front row, are the powerhouses of British astrophysics: Eddington, Milne, Fowler, and Jeans. In the chair is Frank Stratton, president of the Royal Astronomical Society and professor of astrophysics at Cambridge, and Chandra is in a state of nervous excitement. He's about to present the definitive version of his theory on nothing less than the fate of the stars, and he has the support of the great Eddington. He takes a moment to arrange his notes, reaches the podium, takes a moment to arrange his notes, and launches into his lecture, Stellar Configurations with Degenerate Cores. He reaches his conclusion. It must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. For a star of small mass, the natural white dwarf stage is an initial step towards complete extinction. A star of large mass, greater than the limiting mass, cannot pass into the white dwarf stage, and one is left speculating on other possibilities. Well, and he illustrated this with his now famous graph, plotting essentially the radius of the stellar configuration with a degenerate core versus the ratio of the mass of the degenerate core versus the critical mass. When that ratio becomes 1, the radius goes to 0, and the star is crushed. Congratulating himself on what he considered to be a superb performance, Chandra gathered up his papers and returned to his seat at the rear of the room next to his pal, Bill McRae. Ever theatrical, Eddington remained seated for a fraction of a minute, rose abruptly from a seat in the front row, mounted the platform in one leap, spun around, and addressed the audience with an arrogant flourish. I do not know whether I shall escape from this meeting alive, but the point of my paper is that there is no such thing as relativistic degeneracy. The thrust of his argument was that the very basis of Chandra's theory was absurd. Physically, that is to say, in reality, there is no such thing as relativistic degeneracy. It was mere mathematics and had nothing at all to do with the stars. Rather, Fowler's theory, he argued, is the correct one. And in fact, Fowler, as Eddington put it, being merely a mathematician, didn't realize that his theory is relativistic. That is to say, relativistic in Eddington's version of relativity, which he had honed during his visits to Chandra's rooms and folded into his fundamental theory. Now, to obtain Fowler's theory from his own version of relativity, Eddington had to play fast and loose with the mathematics of Einstein's accepted version of relativity, putting in equations such as an equation for the electron's total energy, which was a mermaid-like concoction of a non-relativistic kinetic energy, p squared over 2m, and a relativistic mass energy. And Eddington went on to denounce Chandra's theory as stellar buffoonery. Now, Eddington had two personae, one of them as a professor at Cambridge University, where people recall him as teaching in the worst of the Cambridge tradition. He just didn't care. But as a public speaker, he was electrifying. And here he is holding forth at the Kepler Monument in Weil der Stadt, Germany in 1928. No notes, just extemporaneously going at it. So it was no contest. This supercilious man used all his rhetorical abilities to demolish Chandra. He essentially ambushed Chandra. Eddington's presentation was worthy of an Oscar. Laughter and guffaws followed as if on cue. Had Eddington befriended Chandra just to destroy him? Chandra was utterly shocked. He felt as if his world had fallen apart. But when he rose to respond to Eddington, President Stratton ordered him to sit down and moved on to the next speaker. Chandra never forgot that humiliation, and that day blighted his entire life. And none of Chandra's friends in the British astrophysics establishment dared stand up to oppose Eddington, although they murmured in private that what Eddington said seemed rather peculiar. But Eddington had the reputation of arriving at correct conclusions from dubious arguments, so they preferred a wait-and-see attitude. In February, Chandra wrote to Babuji, his father, about the situation. He said, But the scientific politics and stellar structure in the triangular contest, Eddington, Jeans, Milne, strains me as I am in the middle and refuse to take anybody's side, and E.M. and J are all quarreling with my work, but I won't let them have any. Here's the triangle, Chandra in the middle, but Fowler supports me from on top. Well, sort of. Hope all is well. Yours affectionately, S. Chandrasekhar. Chandra's prose improved. Friends of the stature of Niels Bohr, Wolfgang Pauli, Paul Dirac, Werner Heisenberg, and Leon Rosenfeld all urged Chandra to forget about Eddington and get on with his own work. Rosenfeld even dismissed Eddington's criticisms as the wildest nonsense. But Chandra couldn't put them out of his mind. So what happened? In 1926, Eddington suggests black holes, although albeit tongue-in-cheek. In 1930, Chandra substantiated Eddington's suggestion with irrefutable mathematics. At this point, Eddington had at least two choices. He could have complimented the young man on his brilliant work, and as many mentors did and still do, say, let's you and I write it up. The write-up would have been couched in the language of general relativity. Had he done so, given Eddington's immense prestige, in my opinion, black hole physics would have taken off much earlier. Eddington, of course, would have received all the accolades, and Chandra would have been remembered as just an excellent astrophysicist. Not bad. Alternately, Eddington could have launched Chandra on a spectacular career at Oxbridge, much as G.H. Hardy had had in mind for the Indian mathematician Ramanujan. But this would have required a complete change of conceptual framework for Eddington, in which stars could collapse to nothingness. No one, not even Einstein, was willing to accept what is unarguably the most spectacular prediction of general relativity. Here was Eddington and Einstein sitting at Eddington's garden in 1932. At Cambridge, Eddington spoke German, got along well with Einstein. And indeed, in my opinion, Eddington is the forgotten man of this Einstein year. But I suspect there was more to it than that for Eddington, because simply going along with the crowd doesn't solve the problem of why, at every opportunity, he cynically and viciously attacked Chandra. Eddington's lambasting of Milne's and Milne and Jeans just paled in comparison. My research has led me to several conclusions that are like tiles in a mosaic. One of them is as follows. If Chandra's theory was true, then Eddington's fundamental theory was destroyed. Now, Eddington's usually ambitious program in his fundamental theory was to unite quantum theory and general relativity, in which there is no such thing as an isolated, non-interacting particle. But in Chandra's theory of white dwarfs, a white dwarf is comprised of an ideal, relativistically degenerate gas in which interactions between electrons and the nuclei lumbering around in the gas are neglected. For Eddington, this could not be a description of a real star, and Eddington claimed that if interactions were built in, then Chandra's theory would fall apart. Now, this turned out not to be the case, but would not be done in full until the 1960s. But Eddington's persistent criticisms added to everyone's belief at the time and into the 1960s that a star will always blow off enough mass to get below the Chandrasekhar limit. And this served to delay Chandra's discovery of black holes for almost 40 years. Now, physicists always kept an eye on astrophysics, and what were the physicists doing in the 1920s and 1930s? Because they would play a major role. Well, for a while, physicists considered astrophysics to be a backwater profession. They considered it a profession where people dreamed up entirely unrealistic models of stars for the sake of mathematical convenience. The real problem was the source of a star's energy. Once that was solved, then problems of the structure of stars would fall away. Everyone agreed with Eddington, who suggested that nuclear reactions are the source of a star's energy, but until the discovery of the neutron in 1932, there was no nuclear physics. By 1938, nuclear physics was a burgeoning profession, and nuclear physicists were looking for other fields to ply their trade. And so it was that in 1938 in Washington, D.C., two veterans of astrophysics and nuclear physics, George Gamow and Edward Teller, decided that the theme of that year's Conference on Theoretical Physics would be energy production in stars. This is a letter of invitation, from a letter of invitation that Gamow sent to Chandra. In 17 March 1938, Delta Washingtonian will shine. There will be stars and nuclei in a strongly degenerated core. One of the stars invited was Einstein, who really wasn't interested in what was going on. Those who were invited, let me just point to a few of them. There's George Gamow, towering over everybody, writing letters in a Gamovian way. Even towering over the young Hans Bethe is Edward Teller and Chandra. As Gamow recalled, the astrophysicists were rather nervous at this meeting because the physicists were discussing thermonuclear reactions in stars using nuclear physics, and the astrophysicists didn't understand any nuclear physics. As Gamow put it, they were sitting on their astronomical things. Bethe, by the time of the meeting, Bethe was already on his way to cracking the problem of energy production in stars, which he did by the end of 1938 for all stars on the main sequence. Meanwhile, what was Chandra doing? Well, in September 1936, after being away for 6 years from India, Chandra returned and married his university sweetheart, Lalita. The following month, in October, they returned, they left India. Here they are in the docks at Bombay with Chandra's family, Lalita and Chandra with his family and part of her family. And Chandra was on his way to the United States. He had been hired to be an astrophysicist at the Yerkes Observatory in Williams Bay, Wisconsin. Yerkes is part of the University of Chicago. Chandra had been hired by Yerkes' dynamic new director, Otto Struve, who hired Chandra and 2 other young astrophysicists, who I'll mention in a moment, to raise Yerkes back to being #1, not only in the United States, but in the world. The next big pre-war astrophysics conference that Chandra attended was in Paris from 17 to 23 July 1938. Just to mention a few here, here's Frank Stratton, who was in the chair that day, 11 January 1935. Henry Norris Russell, the Dean of American Astrophysics. Gerard Kuiper from the Netherlands, and Bengt Strömgren from Copenhagen. The 2 others hired along with Chandra. Here's Walter Baade. And here's Eddington with a sardonic look in his face, looking his rumpled best. And Chandra looking rather unhappy, having been beaten up intellectually earlier in the day by Eddington. Now at the meeting, Chandra immediately took the high ground and wrote and said that everyone agrees that that an equation of state for a relativistically degenerate gas of electrons is the proper one for a white dwarf. Eddington responded, he disagreed. Fowler's was the only theory. Fowler solved the problem. Chandra reopened it with a bunch of mathematics. Gerard Kuiper, the premier observational astronomer of white dwarf stars, presented data to the effect that the mass of most known white dwarfs were on the order of the mass of the sun, in agreement with Chandra's theory. And their radii was small, which was in disagreement with Fowler's theory, the hallmark equation of which was the product of a white dwarf's mass and volume is a constant. So white dwarfs with a very small radius should have a huge mass, like 1,000, 1 million solar masses, and that was not found to be the case. Eddington went on to defend Fowler's theory, calling for more exact data. And perhaps there need be modifications in Fowler's theory, and then Eddington turned to extreme cases, as he called them, white dwarfs that are very, very small, whose masses were not yet completely determined. Eddington noted that it would be good to apply Fowler's theory to these small stars. You can see how it should be modified. But these small stars are interesting also in that they were so small and therefore so dense, maybe of nuclear density, that the electrons and protons in them would be forced so close together as to form neutrons. There would be a neutron star, an object which had been hypothesized in 1933 by Fritz Zwicky and Walter Baade. And that would be another step preventing complete collapse if a star went through a white dwarf. At the end of the conference, Eddington and Chandra found themselves in the same room alone, and Eddington turned to Chandra and said, "I hope I haven't hurt you." And Chandra replied, "Have you changed your mind?" To which Eddington said, "No." And then Chandra replied angrily to that, "Well, I feel sorry for you," and abruptly turned around and walked away. That was their last face-to-face meeting. Chandra left the field of stellar structure. He was disgusted. He felt he was like Don Quixote tilting at windmills. He didn't need to convince anyone of the validity of his theory. And as his parting motion to the field, he wrote an introduction to the study of stellar structure, a book still on the desk of every astrophysicist. When Eddington saw the book, Eddington quipped, "Isn't it nice to have all the wrong results in one place?" Their uneasy relationship continued. They corresponded, Chandra from the United States, Eddington in Cambridge, but still a constitution of stars was never discussed. Eddington died of a cancerous stomach tumor in a nursing home under pitiable conditions in November 1944 amidst the privations of war. Chandra launched on a series of 5-year plans. He turned first to the study of radiative transfer, and then to such highly mathematical subjects as hydrodynamic and hydromagnetic stability, subjects that Chandra called the high school of British mathematical physics, with people in it such as Lord Rayleigh, with whom Chandra often compared himself. Indeed, Chandra had always wanted to become a mathematician, just like Ramanujan. And in diary entries and letters to personal friends, he lamented that he was a reluctant astrophysicist. He just hated calculating all those numbers. Soon after the Paris Conference, World War II broke out. During the war, Chandra's defense work concerned ballistic problems at the Aberdeen Proving Grounds in Maryland. For various reasons, not moral, he declined to work on the atomic bomb, on the Manhattan Project. But scientists involved in the Manhattan Project, in particular those involved in implosion mechanisms, found themselves studying the fate of stars and astrophysics. And in doing so, they realized the intimate connection between exploding stars and exploding bombs. In both cases, radiation tries to find its way out through nuclear matter, so the problem of opacity pops up. If the radiation escapes too easily, the bomb will fizzle, the star will burn out too quickly. If the radiation is constrained too much, the bomb will explode prematurely, and so will a star. So thus, two of Chandra's specialties became important for the Manhattan Project, radiation transfer and hydrodynamic and hydromagnetic stability. That is the study of flow, of shock waves, of how to compress matter and blow it up. By 1942, Edward Teller, a veteran of astrophysics, as I mentioned, realized that the temperature of an exploding fission bomb is just right to ignite fusion of hydrogen, and therefore there arose the possibility of a bomb even more powerful than a fission bomb, the super. High-speed computers were necessary for simulations. There were not going to be any laboratory tabletop experiments for this one. After the war, high-speed calculators became available, but regarding stars, it was still incumbent upon someone to cook up a reasonable model of a star and then blow it up. John Wheeler, who had extensive experience in bombs and nuclear physics, had at his disposal at Princeton University one of the most powerful digital computer on the planet, the MANIAC mathematical analyzer, numerical integrator, and computer. And Wheeler came to the conclusion that the fundamental problem in science is the fate of large masses. In the 1950s, with two graduate students, Harrison and Wakano, Wheeler programmed into the MANIAC the most advanced equation of state that one can have, that contained relativity and also all up-to-date nuclear physics. And they studied cold matter, that is the burnt-out core of a star, and what happened over large regions of densities and pressures. And they input data from just about every known star into their equation, into their computer, and found essentially this is how much you compress it, This is the density, and there are 2 way stations, a white dwarf star, and then at nuclear densities, you can have an object made up mostly of neutrons, the still hypothetical neutron star. They also found out that, something else can happen here. If a star is big enough, it can crash through all known degenerate cores and collapse into nothing. And we'll just refuse to believe this. Enter Sterling Colgate. Colgate is a figure, little-known figure to the outside world, who rose to prominence in the Livermore, Los Alamos community. He was America's premier diagnostician of nuclear weapons. I'm speaking now of the days of the Mike and Bravo tests of 1952 and 1954. This time around, Chandra contributed to research, bomb research in Los Alamos and Livermore, and played a part in the Mike test of 1 November 1952, a 10 megaton yield which made the Hiroshima and Nagasaki bombs look like firecrackers. And also in the weaponized Bravo test of 1954. Now, Colgate's interest in supernovae dates to the late 1950s because their highly energetic radiation could trigger the sensors in spy satellites that Colgate had helped to design, which was set up by the United States to detect Soviet nuclear bomb tests, and this could start World War III. Now, a supernova is a star, heavier than about 15 times the mass of the sun, which collapses. And when it collapses and crushes its core, it's like a gravity bomb. It ignites, sets off light to the order of to a brightness of about 1 billion times the brightness of the sun. Let me just summarize the fate of a star. This is of a star 18 times the mass of the sun. It begins as a gas cloud, begins burning hydrogen. Star that heavy burns out fast. Our sun burns out more slowly, good for us. This star has had it after about 16 million years. And then it goes through paroxysms of a series of burnings. And finally, what you have left is a silicon core, 4,000 kilometers in radius, around an iron core, 850 kilometers in radius, and above it is this huge amount of nuclear material weighing millions of tons, pressing on it until, bang, it compresses it. Core compression. The silicon core, 8,000 kilometers in diameter, gets compressed to 20 kilometers, and this is the way, I'm talking about the way things were understood in the 1950s, 1960s. Eventually, the core cannot be compressed any longer. It's like compressing a rubber ball. It gets to a point where it bounces out, and you get what's called core bounce. And the result of core bounce is a supersonic shock wave traveling out at 6,000 miles per second with a hot shock front. And what that hot shock front is supposed to do is smash into the infalling nuclear matter and blow up the star. That all sounds great, but just fizzles were gotten from these computer simulations. Colgate was involved in some of these abortive attempts, and finally, in 1960, Colgate and his co-worker Richard White set out to devise a new equation of state for a star on the verge of collapse. They had at their fingertips the most powerful computers in the world at Livermore, and their new equation of state was unique in the sense that it comprised not only astrophysics codes, and this is for an ideal gas. This is for a gas of electrons now. A relativistically degenerate gas of electrons with interactions built in. So it had everything. General relativity, special relativity, and also radiative transfer codes and hydrodynamic and hydromagnetic stability codes, shock waves, that is to say, from hydrogen bomb development. They were permitted to do this. Colgate's brainstorm was to blow up a star with neutrinos. Now, neutrinos are manufactured inside stars by electrons smashing into nuclear matter, and there are lots of them produced, one with 51 zeros after it, 10 to the 51 neutrinos. And these neutrinos are supposed to add further push to the hot shock front to make it blast through the nuclear matter. And in fact, they found out something else, that pretty definitively, that if a star is heavy enough, it could go on collapsing. It could smash through all the electron degenerate core, the neutron degenerate core, any other core you could think of, and be crushed into nothingness. Wheeler made several trips to Livermore, a lot of trips per year to Livermore, and when Colgate told these results to him, he was dumbfounded. Wheeler's opinion on the state of how a star could expire radically changed. Now, Colgate and White wrote up their results in one of the most quoted papers in astrophysics. And they sent it to the editors of to the Reviews of Modern Physics. This is a long paper, and there it sat for 3 years on the editor's desk. After all, what one had was an astrophysics paper written in the language of physics, which made no sense. And so finally, the editors of the Reviews of Modern Physics sent it to the editor of the Astrophysical Journal, who was Chandra. Chandra took one look at it, realized this is really important, and also it substantiated his discovery. Stars could actually collapse. And what he did was he wrote a letter to Colgate and said, Sterling, you just have to learn some astrophysics. But what Chandra did was to rewrite it and take the editor's prerogative, and at least at one point, and added his own book to stand next to Eddington's. In the end, the Colgate-White work was a magnificent failure. They did the best they could. Even their model was a fizzle. There were a couple of things left out. Chief among them was the electroweak theory, a theory that unifies quantum electrodynamics and weak interactions. This theory gives an added role to neutrinos. What was also left out is that they simply didn't have enough computing power. The most powerful computers in the world weren't powerful enough. Now, other scenarios for blowing up a supernova were proposed over the years, but the neutrino scenario was a very attractive one. But that it should be at all true was not verified until 24 February 1987, when Ian Shelton, an astronomer, Canadian astronomer at the Las Campanas Observatory in Chile, looked at some plates he had taken earlier that morning of the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, and saw a bright spot. It could only have been a supernova. But he remembered he had photographed that area of the sky not too long ago, in fact, the previous day. And there was just a spot there. And what happened was that this hapless star, Sandalac 69°202, had blown up and gone supernova. This was the first, Shelton stepped outside of the observation shack, looked up into the sky, the daylight sky, and there it was. That was the first supernova observed with the naked eye since 1604, observed by Johannes Kepler. Neutrinos were picked up from it at two observatories, Kamiokande in Gifu in Japan, and IMB at Fairfield in Ohio. The year after the Colgate White paper appeared, this is in 1967, Jocelyn Bell and Anthony Hewish spotted a pulsar in the Crab Nebula, which is in the constellation Taurus. The Crab is 6,000 light years away. It was a momentous event. Along with ongoing theoretical developments by Roger Penrose, everyone was prepared for there to be another way for a star to expire besides a white dwarf and a neutron star, that is, a black hole. Wheeler became a convert. Here he is lecturing in 1971 on black holes. In 1972, the first black hole was spotted. It's not this, it's another hapless star, HTE 226868, and the black hole is a highly irregular, very powerful X-ray source, which is a binary companion of HTE 26868. Here is an artist's rendition of it. That's all you can have is artist renditions of these things. And Cygnus X1, 3,000 light years away, is from us, is siphoning off gas. It's from its binary companion, eating it up, forcing the gas into a swirling disk, and looking at it closer, it looks like this, the black hole that I showed you at the beginning of the lecture. Since then, many more black holes have been spotted. By 1972, Chandra had re-entered the field of stellar structure and had begun exploring black holes. But he had missed the boat in the field that he had essentially started. The big work had been done by others. On October 19th, 1973, the day of his 73rd birthday, Chandra was informed that he had won the Nobel Prize, along with Willie Fowler, the astrophysicist at Caltech. Chandra, however, was ambivalent over this. Because after all, he said it was for a discovery that he made when he was a mere lad on ship crossing the Arabian Sea. What about the rest of his life's work? Up to that time, Chandra had been complaining that no one recognized his original discovery. Now, Chandra seldom discussed his turbulent state of mind. His public persona was that he had put the Eddington episode behind him. And indeed, Eddington had done him a favor. He had hardened him. He had become inured in an Eddingtonian furnace. But diary entries, letters to certain select people, and interviews with friends reveals another story. For Chandra, it became an obsessive quest to prove that he was a better astrophysicist than Eddington, or at least as good an astrophysicist as Eddington. The story of Chandra and Eddington reminds us that science is a human endeavor, driven by hopes, dreams, and aspirations, especially at its highest level, where scientists strive after the highest stakes. These people may be brilliant, some may even be considered as geniuses, but as human beings, they may even be seriously flawed. And such was Chandra and Eddington. It is apropos to bring the story of black holes to a conclusion with some data from some spectacular data from the Chandra X-ray Observatory. Placed in orbit in 1999, 4 years after Chandra's death, its mission was to search for black holes, and it has been immensely successful. And in my opinion, the most amazing picture is the so-called deep sky survey of the center of our galaxy, the Milky Way, which was completed in July 2001. It's some trillions of miles wide by trillions of miles high. And in the center is, as hypothesized, every galaxy should have its black hole, is our black hole, Sagittarius A star, some 26,000 light years away. This is an interesting photograph. It's an artist's rendition of a star, which is the orange circle. This episode is taking place 700 million light years from us, and it's one of the most lopsided battles ever seen in the cosmos. It's a star about 1 stellar mass that wandered too close to 100 million stellar mass black hole. What happens is that the star got spaghettified, just like the astronaut I showed you at the beginning, and then ripped apart. And the black hole gobbles up a lot of gas that comes out of it, and the rest of it is thrown out into the galactic suburbs. This is data taken by the Chandra X-ray satellite in conjunction, as space telescopes often do. They work in conjunction with other satellites, in conjunction with the Rosat X-ray satellite, a German satellite, now defunct, and the European Space Agency's XMM Newton. This is a planetary nebula, NGC 6751. This is from data taken by the Hubble Space Telescope. It's 6,000 light years away in the constellation Aquila. And a planetary nebula is a glowing cloud of gas formed when a relatively low-mass star, like our star, reaches its later years in life, burned out as hydrogen, then the outer layers lift off. And in the core is comprised mostly of carbon with some oxygen, with a layer of hydrogen and helium. And as the core, and it will eventually cool down and become a white dwarf star. since its core will be, in the end, mainly crystallized carbon, it will be a diamond in the sky, a fitting end to a star that led to great discoveries and changed the lives of two men. Actually, one of these objects, of course, when a white star becomes a real white dwarf, we can't see it any longer, but one that's pretty much dark and almost crystallized was spotted recently. It's 50 light years from us with the innocuous name of BPM 37093, and it's been assessed as a diamond in the sky of 30 billion trillion carats, and it was named Lucy after the Beatles song. This is NGC, the galaxy NGC 6240. It's actually a composite galaxy, 3,000 light years away, made up of two galaxies that have collided with each other some million years ago, and they merged. It's in the constellation Ophiuchus, and the optical data were taken by Hubble, and the X-ray data in blue, these are all false colors, of course, were taken by the Chandra X-ray satellite. And these two are two black holes coming towards, there are right now they're 3,000 light years apart. They're moving towards one another, spiraling around one another in this deadly tango. They're in-spiraling, and in some 400 million years, they will combine into a single black hole, and then they will snap into place as a single black hole, and there will hopefully be a tsunami in space-time of gravitational waves, which will be, well, we're not going to wait 400 million years for that to happen, but there are a few events like that, like this a year, that are supposedly going on in the universe, and the gravitational waves, a still unconfirmed prediction of Einstein's theory, will hopefully be picked up by LIGO, the Laser Interferometer Gravitational Wave Observer, earthbound, 2 arms, 2 miles long, laser beams going back and forth with a giant interferometer. There are 2 of them, one in Hanford, Washington, and one in Livingston, Louisiana, hopefully still above water. And then in 2017, LISA will be launched, Laser Interferometer Space Antenna, comprised of 3 spaceships, 5,000 kilometers apart, exchanging laser beams. Now, that's pretty spectacular. Let's go down to Earth. This is CERN, nestled in front of the Jura Mountains, and this dotted line is dotted circle gives you the tunnel, which is underground, of a Large Hadron Collider. This is one part of it. In these pipes, 2 oppositely directed beams of protons will go around at enormously high speeds. Then it will be brought together, and it will be smash-up time at CERN. And now, a lot of physicists consider this to be just pie in the sky, advertising for high-energy physics, but that's not the point. The point here is that black holes are being discussed as being produced in the laboratory. Objects that were considered to be an ugly solution to a beautiful theory are, number one, now beautiful, and deemed beautiful, and number 2, they're inside of equations. Here we have, well, PP are partons, because the protons get blasted apart. So 2 partons go to a BH, just like EP, beryllium, whatever, a black hole, plus other stuff. That's rather nice. So we have a recipe for making black holes. You mix together protons moving at very high speeds. Result, energy concentrated in a very small volume. According to Einstein's 4th great paper of 1905, energy is equivalent to mass. So you have a mass concentrated in a very small volume, the size of the mass's Schwarzschild radius. Black hole, that's it. And these black holes have a mass of about the proton, very light, so they'll be very hot, and so they should decay very fast into Hawking radiation. And physicists hope that from the shape of the radiation spectrum, one could determine the number of dimensions in space-time right after the Big Bang, because after all, what you're doing now is creating conditions just after the Big Bang. And maybe there'll be 11, and string theory will be okay. Who knows? So, in conclusion, in the end, Chandra is vindicated many times over, Eddington proven wrong. What I've given you is just the outline of a very complicated story, which is told in detail in my recent book. I thank you. If you have any questions, I'll be here afterwards, too. In fact, I'll be here all week. Thank you. Okay. Are there any questions?
¿Cree usted que los agujeros negros...
I can't hear.
Pregunto su opinión sobre el futuro de un agujero negro si llega a evaporarse y deja de ser negro.
It evaporates into...
Radiación.
Yeah, that's a good question. It evaporates into elementary particles and light. You have to wait a long time for heavy black holes to evaporate, maybe even longer than the age of the universe. But black holes produced in the laboratory, they will evaporate instantaneously, so you don't have to be afraid of being sucked up by one. Thank you. Thank you. Thank you very much.